And our next speaker is Alessio Bernardo. Alessio, are you here? Can you hear us?
Yeah, thank you. Hello, everyone.
Perfect. Hi, Alessio. So Alessio is a research fellow at Politecnico di Milano in Italy, and he's working on streaming edge AI. So what's streaming AI, what's streaming machine learning, concept drift, class imbalance, evolving data streams? I'm just tossing random keywords here, and how this is connected to the River library. So Alessio is gonna give us a very nice introduction about this popular library. And so Alessio, when you want, the stage is yours.
Yeah, thank you very much. Do you see my screen?
Yes.
Okay, thank you. So I can start. So as Andrea was saying about me, I am a research fellow at Politecnico di Milano, and I am also a co-founder of a startup related to these, let's say, these keywords that Andrea introduced before. And in particular, my research and what I'm doing right now is something about streaming machine learning in case of evolving data streams, concept drift, and class imbalance. And all these keywords, I introduced them during my presentation and my tutorial. And last point is that right now I'm focusing on applying these techniques on constrained environment in the network edge. So we live in a streaming world, and so we have data everywhere produced from smart sensors, smart cities, industrial IoT sensors, and so on. So we have a lot of data, but almost 68% of them are not used. So a lot of data, but we don't know how to use them right now. By 2025, we will generate up to 175 zettabytes of data, but we can see on the other figure that the 44% of them goes uncaptured, and the 56% are captured, but only the 33% of them are here. Only the 57, sorry, are really used. So in total, we only use the 32% of the data generated. So we have to, let's say, introduce some new approaches to be able to really use all the data generated. From one side, there are the traditional approaches to analyze the data. So we stop the data at some point in time, we collect them in a repository, and then we apply some techniques. And this is the traditional machine learning models. So we have a batch, we split it into the training and testing sets, and then we train a model on the training and we test it on the test sets. And in the end, we have our prediction. But there is the need to a new approach that is able to handle the velocity of the data that are generated right now. So instead of stop the data, at some point in time, we need an approach to a velocity approach, so to analyze the data in motion. And this approach are the streaming machine learning techniques. So this is one of the approaches, of course, but so this is also what I'm researching it. So instead of having a static batch of data, we have a data stream that is unbounded. So every moment in the time we have new data, new samples. And first of all, we use streaming machine learning models to predict, so to make some prediction with the new data, and then we incremental update it, so one sample at a time. So this is a paradigmical shift respect to the traditional train and test phases. So just to do a brief recap on what streaming machine learning models are. So these models are incremental, meaning that they are able to learn some samples or one sample at a time. And in this way, they are able to take into account the unboundedness of the real-time data, and also in a resource-efficient way, because since the data are unbounded, it's unfeasible to store all of them in memory, of course. And these models, after the testing and then the training phase, discard the samples because they have already, let's say, learned from them. And last important point is that these models, or at least some of these models, are dynamic, meaning that they are able to adapt to some form of non-stationarity. And then that I can introduce it in a moment. let's see before which are the benefits and the challenges of these models. So from the benefits, for sure that there is that they are able to learn one sample at a time and in an incremental way. And this leads to time and memory management. But of course, the challenges are the data stationarity. So if data can change over time, and this is called concept drift. So this is an important keyword. And another one is the class imbalance. Of course, over time, also the class distribution may shift. And the last one is the hyperparameter tuning, meaning that it's difficult to find some parameters that can be still valid for all the time with all the data generated. And for this tutorial, I'll focus only on concept drift, and I leave apart the class imbalance and hyperparameter tuning, of course. But I mean, if you have questions in the end, I can I can answer to them. And so let's see, what is concept drift. Usually, when I try to explain concept drift, I start from these two type of examples. So the first one is that it comes from COVID. So before the COVID, we all have some habits, and after that, so when we were, say, forcibly at home, our habits changed. And for example, if you think about a recommender system of Amazon or something like that, that was used to recommend some stuff at that point of the year. So it was at the beginning of spring, and due to some habits of the people in that period of year, and so, for example, recommend something to go for an hike or to stay in the fresh air. And after the COVID, those recommendations were totally wrong, because we were forced to stay at home. And so this is an example of concept drift. Our habits changed, so also the data that we generated changed, but the Amazon recommended system didn't know it, and because it was, let's say, a static model. And so let's say, he continued to predict something that was totally wrong. So this is a clear example of concept drift, because so a paradigmatical shift of the data. And so this brings to the light the need of new models that were able to adapt to new data, to new characteristics of the data. And in fact, Gartner put this concept brief, and in particular, he called the adaptive artificial intelligence systems, into the 12 data and analytics trends in 2022. Giving a little bit into details, this is a very simple example. And so over time, there is a concept drift when there is a change of the statistic of the distribution. So here we have let's say, two clear type of distribution. So the blue one and the orange one. And here the concept drift is when we shift from one distribution to another one. But so which are the consequences of concept drift? Here, the concept drift is represented by the red line, and if our model is not able to adapt to the concept drift, we can see that its its accuracy goes down. Instead, because it doesn't recognize that something is changed into the data, and the model predicts something that is not true anymore. Instead, if it is able to detect the drift, then its performance can stay high. So, in order to address the concept drift problem, let's say a little piece of so a little mechanism was created, was proposed into the infrastructure of the train and then test phase. And in particular, it was introduced the change detector, this module that has the responsibility to detect some changes and to raise an alarm. And another, let's say, more concrete example of about concept drift is, for example, the weather forecast. So we all know that the nature is is a chaotic, and also in this in the last few months we know that something's changed in the climate, and so there is a clear example of constant drift. So the weather forecast model must detect these changes that can be abrupt or maybe also gradual, but they are always changes, and they must be able to adapt to them. So, and without to be retrained from scratch usually. Of course, this is not always true, because we know that weather forecasts in the last period always, let's say, fails. But let's say this is another a real example. So this was just a brief introduction about streaming machine learning and concept brief. And now we can move to the code. And you can, if you scan this code, this QR code, you can go to a GitHub page, which I load this presentation and also the two notebooks that right now I'm going to show with you. And I think that also Andrea put this link on the conference webpage. And to run, if you want to run these notebooks, I used Anaconda, and I put here some command to create a virtual environment and to install some packets into the requirement file. But I think that I think it's better now to just to follow me, since the time is strict, and then you can replicate all the code. So the two notebooks are in the notebook folder, of course. And so in the first one, I'll show you how to start from scikit-learn, so from a classical machine learning model in a scikit-learn, and to transform it into a river model. And river is the most used streaming machine learning library in Python. While in the second notebook, I'll show you how to use some models and metrics with two real world tasks. So for the first notebook, I use the ARIS dataset, and that is pretty common in scikit-learn. So we have three different types of irises, so the versicolor, the setosa, and the virginica. And the task here is to predict which type of iris is that flower based on the sepal width and sepal length. So here I just load from scikit-learn the iris dataset, and I splitted the feature from the target into the X and Y variable. And with the train test split function of the scikit-learn, I also let's say splitted from in training and testing phase. And I use the 30% of division between the two of them. And just for, let's say, simplicity, here I'm using a Gaussian Navi-based model from scikit-learn, and with the fit function, I fitted the model. And then with the prediction, we can do some prediction. And then I just printed the accuracy, just for simplicity. So here we can see that the accuracy of this model is the 91%. So until now, I think that I assume that is all clear, because it's the standard way to train and test a model. So, but right now, let's see how to transform this standard phase into a streaming phase. So first of all, with River, we don't have all the data available. So we don't have a training and a testing set, but we assume to have only one sample at a time. And so we have, let's say, this stream that flows over time. And in particular, River works with dictionary. So in input, it wants a dictionary. So let's say the simple thing to have a dictionary from our train structure that we created before is just to do a for loop and to zip it. And so this is a single a single row. Okay, this is our single sample with the dictionary. So if we have the dict with the zip, and this is what Rivers wants an input. So the name of the feature with the value, and then the class. So let's do another step. From River, I use the Gaussian Navi bias. That is, let's say, the same model, but it is rewritten in order to be used with one sample at a time. So in this library, you will find the major part of the machine learning methods. So Gaussian models, tree models, ensemble models, and in the last time also some neural network models that let's say they statistically they are based on the traditional models, so the traditional counterpart, but they are all adapted to work with one sample or few samples at a time. So in this case, this Gaussian Navi bias is written to work with one sample at a time. So after importing it, and I iterate on the train set, and I create the dictionary, and with the learn one function, I train the model. And then for the testing phase, I iterate over the testing set, I create my dictionary, and then with the predict one function, I take the prediction. And if I print my accuracy, we can see that this is the same. So this is the proof that the Gaussian Navi bias model in River performs as the one in scikit-learn. And this is the first, let's say, a first proof. But let's see. So we have also some other steps to do. First of all, here we started from the train and the testing set, okay, that we loaded before, but we all know that we don't have this possibility with streaming machine learning, because we have a flow of data, so a data stream with only one sample at a time. So River allows us to use the other scikit-learn dataset function, and in this way you can load directly the dataset. You can decide if to shuffle it or not, but let's say you have directly the X and Y, so all the feature and your label, one sample at a time. So you don't have anymore the division in training and testing. So for every time, so for every sample, right now you do the prediction, because in streaming machine learning, the prediction comes first to the training phase, because we have the necessity to predict, so to predict the new label before, of course, giving the new sampling input to the model. Otherwise, you will overfit the model. And so, first of all, use the predict one, and then the learn one. And just for now, we continue to append the true label and the predicted label. And also in this case, we can see that we have the same level of accuracy, so 91%. It is a little bit higher. You can see that one, because of course the two type of methods, so the original one and the incremental one, so the River one, are share the same statistical foundation, but since the River one works with only one sample at a time, in the end can have a little bit of let's say differences in the statistical in the matrix, in the final matrix, and this is due to the fact that it sees one sample at a time and not all the samples in an only way. Okay, so the next step is to avoid to append all the true labels and the predicted labels in a list, and then to use the accuracy score from scikit-learn. In fact, also the metrics, the way in which the metrics are are computed is changed because they are also incremental. And so in River, you will find also a set of metrics computed in an incremental way, so one at a time. So here, instead of saving all the samples, all the label and the predicted labels in a list, you can import your metric and use the update function. And in the end, you will have your metric. That is always, it is the same. You can also compare the confusion matrix. So this is the scikit-learn confusion matrix method, while for River, each metric has the confusion matrix attribute, and you can compare them, and they are completely the same. So to redo all the experiment, here we have, so we learn to load directly a data stream with the iter scap learn dataset. We learn that we have to first recompute the prediction, so with the predict one. Then we update our metric, so giving the input the true label and the predicted label. And then we update our model with the learned one. And in the end, we have always the same performance, so the 91.95% of accuracy. And the last step, River introduced another method that is the progressive validation score that does all this stuff for us. So calling this function, you have to give in input only your stream, the model that you want to test, the metric that you want to test, and you can also decide if you want to print the result every some iteration. So here I load my dataset, I define my model and my metric, and I give all to them in input to the progressive val score. And here I told him to print my result every 10 iteration. And so every 10 samples in input, it prints out the incremental accuracy, okay? And in the end, it comes out that, so with the 91.95%. Everything clear? Do you have any question? Of course, don't interrupt me, and don't worry. Otherwise,
so far so good.
Yeah, we can go on. But I mean, if you have any question, it's better to ask them, because then the things goes a little bit harder. Okay, so everything is clear. We can go to the second notebook, and here I show you some classification methods, the most popular one, and use it with two different datasets. And the first one is the new weather dataset. So here the task is to predict if the weather will be raining or not, based on some features, so the temperature, the sea level, the visibility, and so on. And the particularity of this dataset is that it is static, so the data distribution does not change. While on the other dataset, there will be some concept drift. So we will compare some models, in this case classification models, and we will see if some models are good in some cases and not in some others. So in these cases, so you will find these two datasets directly on the GitHub repository, and the label is on the last column. And you can also, instead of load directly your dataset from scikit-learn, you can use the function iterpandas, because here I load my dataset with pandas. And with iterpandas, you can specify in input which are the features and what is your label, and then you have your object that is the string. And then you can go with the progressive validation score function that I showed you before and test all the models and metrics that you want. The first model tested here is, again, the Gaussian Navi bias. And for the metrics, you can also test more metrics at the same time. So here I created this object called metrics and I passed it a list of metrics that I want to use. So here I use the accuracy, the balanced accuracy, the geometric mean, and the coin kappa. And then I passed all this stuff to my progressive validation score method, and I print the result every 1000 instances. And these are the results. So you can see that the metrics start, let's say, growing usually. In this case, not all of them grows. And in the end, you have the final value of the matrix, and that you can compare with the others. The second method tested here is the KNN classifier. So it's the common adaptation, is the adaptation to of the common KNN classifier. But instead of having all the samples to compute the neighbors, it takes a window of samples, and you can define the length of these windows and compute the neighbors across this window. And so here you can also specify the number of neighbors, but there are also some other parameters. And if you click on the name, there are all the links, and that goes to the API of River, and you can see all the explanation of the models and all the upper parameters that you can set. And here all the setting is always the same. I changed only the model definition. So if I run this shell, we can see how the KNN classifier performs. For sure, you can see that it's more slower. It's slower than Navi bias, but I mean, this also happens, I think, in the traditional implementation of KNN classifier. So let's see in the end which are the results. Okay, maybe in the meantime, I can start explaining also the other models, and then we can review all the results together. So the third model is an off-feeding tree. Off-feeding tree is the incremental adaptation of the common decision tree. And in particular, it uses the off-feeding bound to decide when to make a split on the data or not. And this off-feeding bound is a statistical method, and so it has statistical proof that when you split your node, you are doing the right thing. And of course, it has different upper parameters to set, but in this case, I use all the standard ones. Another method is the off-feeding adaptive tree. So here we are going into the direction of concept brief. So the difference between off-feeding tree and off-feeding adaptive tree is that at every node, the off-feeding adaptive tree uses a concept brief detector. So at every node of our tree, we have this method that is called adwin that is able detects changes. So if there are any changes, and if there are, it starts growing in parallel another branch of the tree. And then when it is sure that a drift happens, it switches the two branches of the tree. So over time, this model is able to adapt to concept brief. And then we will also compare in case of concept brief, then we will see the difference. And the last two ones instead are ensemble methods. So the first one is the data random forest, and it is the streaming version of the random forest. So the ensemble of off-feeding adaptive tree. So here we have different off-feeding adaptive trees in an ensemble. In this case, I use 10 off-feeding adaptive tree. And say the way which it works is the same as the random forest, but in a streaming way. While the second ensemble method here is the streaming random patches. In the streaming random patches, you can define which model to use as a base learner. In this case, I use an off-within tree. But the difference with respect to the adaptive random forest is that it simulates the random subspaces. So you can define with some parameters which samples to use or not with random subspaces. And let's see also the results before going on. Now adaptive random forest is working, and we can start comparing the previous results. So let's take into account, for example, the accuracy. The Navi bias achieves the 69% of accuracy, and we can see that the KNN is much more accurate with the 77%, and is also more accurate than the off-within tree. So it's probably due to how the let's say the data are so the statistical data are done, because usually the trees are much more performant than the KNN. And another thing to notice is that there is no difference in this case between the off-within adaptive tree and the off-within tree, meaning that really the data stream is static and stationary, because we achieve the same performance. And then with the adaptive random forest, we achieved a 78% of accuracy, so higher also with respect to the KNN, as we expected. And then let's see about the streaming random patches, what happens. But I expect something similar or better with respect to the adaptive random forest. And let's see. In the meantime, I introduce you the last dataset, that is the Agraval. Here the task is to predict if someone will have a loan or not based on this feature. And in this case, here we have a concept drift. Okay, so we have two gradual drifts. So at the 5,000, 10,000, and 15,000 sample. And another things to notice is that we have also some categorical features. So if you want to, let's say, implement and test some methods, remember this stuff. And here I replicated pretty the same models as before, and just to show you how the performance can change with the concept brief and which model is the best. In the meantime, here the stream random patches ends, and it achieves the 78% of accuracy, so it's a little bit better than random. So going down to the concept brief, here we can see that, for example, at the 5,500 sample, the accuracy drops down from 86% to 46%. So something happens, and the Navi bias doesn't have any concept drift detector inside, and so the accuracy drops down, and also all the others. And then we can see that it still goes down for some samples until finally it was able to recover, let's say, itself over time. But then another drift occurs here, and the performance drops down. So this Navi bias is an example of a non-dynamic model. So it is static because it doesn't use any concept drift detector. Then for the off-within tree, this is the same, because also the off-within tree does not use any concept drift detector. So here you can see the same behavior at the 5,500 sample. So the performance drops down from 90% to 55%. And here is the same. And in the end, it achieves the 66% of accuracy. So this is much better than the Navi bias. But let's see now how the off-within adaptive tree, the adaptive random forest, and the streaming random patches performs, because these three models implements a concept drift detector inside. So instead, here we can see that still it suffers from, let's say, from the change, but in a fewer way, so in a slighter way with respect to the off-within tree. And in fact, in the end, it achieves the 68% of accuracy with respect to the 66. So here the concept brief, the change detector, let's say, did this work, and it was able to, let's say, mm, to detect the drift and to adapt the model faster with respect to the off-feeding tree. Okay, so of course it doesn't work instantaneously, the change detector, but it takes some time to detect a drift, and when it detects it, it makes the model to adapt, of course, but it's not instantaneously. And let's see the data random forest. We can see that here the performance goes up again. So it performs 75% of accuracy. Oh no, sorry. It's they were worse. So this is for sure a case to investigate if you want to maybe to investigate more. Probably you have to change some hyperparameter values. If you use more models, you will achieve higher results. And then we will see also the semi-random patches that uses a concept drift detector, what we'll achieve. Okay, it's almost the end.
And so in this benchmark, the drift is gradual, you mentioned, right?
Yeah, if I suppose,
Okay,
if I remember
okay.
well.
No, that's
Yeah,
interesting. I was
yeah, it's a gradual
I
drift.
was expecting a lower drop in accuracy given the gradual drift, because in continual learning we are used to sudden drifts, of course, like introducing new classes, and we get like a huge drop. So I was expecting a lower one, but I guess I mean gradual drifts can be tough too.
Yeah, also, but because it's tough, because it's more difficult here in streaming machine learning to detect a gradual drift with respect to an abrupt one, because
Yeah, that's true.
if it is abrupt, your statistics change from one moment to another one, and so the change detector is so for the change detector is more easy to detect it, and so to adapt instantaneously the model. Instead, if it is gradual, it takes more time, and in that time, the performance continue to drop down.
Yeah, provided that you use a detector, which we don't often do in continual learning. But yeah, please go ahead. Thanks for the
No, yeah,
clarification.
yeah, no, it's done. And in this case, also the streaming random patches achieves lower performance. So probably you have to increase the number of models to use to achieve better performance. And I mean, that's all. So these are the most used classification models with concept drift concept drift detector or not in River. And if you go to the website, you can also test some other models and let's say play a little bit. So thank you. And now, if you have any question, I think that we have some time.
Yes, thank you. Thank you for being on time. And that was an interesting presentation on River.
Thank you.
And yes, as I was mentioning right now at the end of your talk, I mean, this really highlights the impact that a concept drift detector can make, because from the perspective of streaming machine learning, probably, I mean, if you have a change in a class, so you have a sudden drift, which is easy to detect, you can exploit this fact and avoid losing so much accuracy like we do in continual learning, because of course we have different assumptions, like we cannot, well, we can in some cases, but we shouldn't allocate separate networks and so on and so forth. So you still have the problem of interference at the feature extractor level, and that's because we use neural networks. So there's a lot of things going on, and I mean, I think that these communities have a lot in common, and also lots of differences, of course. So it was very, very interesting to see how to tackle a benchmark with River and which models you use in streaming machine learning. I've seen a presentation before in which neural networks are also coming into this field.
Yeah.
So I'm also
Exactly.
looking forward to that. It seems a promising way to merge the fields, at least. or at least to start talking.
Start with, yeah.
All right, so we have a couple of questions from the
Yeah.
chat. Martin asks, is there a method in River to obtain ensemble metrics on classifier training using retrained results based on randomized reordering of the input samples? Okay, so this
maybe
might be a little tricky.
It's better to read it.
To get,
read it.
You can see the Q&A, right?
Yeah, okay, the Q&A. Yeah, okay. To the ensemble metric. I think that I don't get your question. Sorry, can you a little bit?
Yeah, Martin, if you can like write
yeah.
either in the chat or open your mic if you want to speak. Perhaps we can go to the next one while we wait. Yeah. So what about benchmarking in River? Is it River used to benchmark for benchmarking purposes? What do you think? Is there another option, or River has like the largest number of models, benchmarks, metrics, and so on?
I think that there are a lot of quite models and also metrics. I think all the most popular ones are implemented here, and for sure the things that is missing is that is the neural network, of course, that are right now quite new, also for machine learning, for streaming machine learning, to the fact that it's difficult to propose an incremental neural network. But I mean, for all the other stuff, I think that there are a lot of methods and also metrics.
Okay, so I guess Marty clarified the question. He meant a measure of sample order sensitivity. So that's pretty interesting because, I mean, in a stream, I guess the sample order matters a lot, right? Or not, I don't know.
Yeah. It matters a lot, but if you are, let's say, if you are referring to the temporal dependence among the data, this task is not properly addressed in streaming machine learning. It's more a task of time series analytics. But I mean, I agree with you that this type of temporal order should be taken into account because it's very important. But right now it's not, and so there is only the assumption that the statistics, so the independence of the data is not true. I mean, so data can change over time.
Yeah. And do you usually in the experiments measure like the performance of your model against different orders of the input stream? For example, if the input stream is just a sequence of images, you can not temporally correlated, so not a video, just like taking MNIST one image at a time.
Mm-hmm.
Do you evaluate the importance of the order of the images? Like, I don't know, probably running the same algorithm 5 times with different random seeds to change the example.
Yeah, yes, there is some sort of k-fold cross-validation. But of course, the stream adaptation of the k-fold cross validation is different because we tend to not let's say change the order, of course, because the orders matter. And so what is done in this type of validation is to assign different weight to that sample, and based on the weight of this sample, you can let's say train your model in different ways, and then in the end you have the same statistical assumption that you did a cross validation. Anyway, I think that this method is available in River, so you can inspect it, how it works.
Great. Thank you so much. Are there any questions? I don't think so. So we are again right on time. This is amazing. This is too easy. So thank you again, Alessio, for this amazing presentation.